Fine, let's start. Okay. So in the last class, I think we have seen some transformations, right? We have seen these concepts, functional transformers, power transformers. Okay. So what's the fundamental point of transformers? To convert any distribution into a normal distribution. Okay. So in this scenario, we have seen specific transformers like log transform, reciprocal transform, and also general transformers like Box-Cox and U-Johnson. Fine. Okay. So now the next concept will be central limit theorem. But before that, actually, we need to cover few important distributions. Okay. Now let's see. So today class, we are saying three types of distributions. One is Bernoulli, one is binomial, and other one is Poisson. Okay, so these three distributions we are going to study. Fine. So let's start with the Bernoulli, guys. Okay, see, simple distributions. Okay, so if not directly, so these are indirectly will be helpful to understand other distributions. Okay, other concepts. Okay, fine. Let's try to understand what is this Bernoulli distribution. Okay, in simple words, okay, this is a discrete type of distribution. Fine. So all the distributions I think we have studied till now, whether it is normal distribution or uniform distribution, or can you help me to remember what type of other distributions we studied?
Log.
Yeah, log distribution, even skewed distribution, right? All these distributions are continuous distributions. Okay, continuous distributions. So when it is continuous distributions, we need to use probability density functions, PDF. Okay, but now Bernoulli distribution is a discrete probability distribution. That means the random variable over here will be discrete. So, and the function, the probability function for the discrete is called PMF, probability mass function. Okay, so the output will be just discrete. Okay, that means countable values, fixed number of values. Okay, so we'll see. It's a type of discrete probability distribution. The Bernoulli distribution essentially models a single trial of flipping a weighted coin. It is a probability distribution of a random variable taking on only two values, value success or failed, with complementary probabilities P and 1 minus P. Okay, so this is the main point of Bernoulli. That means what? In simple words, Bernoulli distribution is the distribution, okay, in which the random variable, that means the output, okay, will take two things always. So one will be success, one will be failure. Okay, one will be success, one will be failure. Okay, and success probability, if you consider it as P, failure will be considered as 1 minus P, because the total probability should be equal to 1. Okay, so any event or any experiment you see where it is having two outcomes, only two outcomes, agree? Where it is having only two outcomes, and it is in this scenario, like the probability of one should be 1 minus the probability of other. Okay, so then that comes under Bernoulli distribution. For example, you are writing an exam. Okay, you are going to pass or you are going to fail. Fine. So probability of pass will be P, probability of fail will be 1 minus P. Okay, you buy a lottery ticket, you will get lottery or not, no lottery. Okay, lottery, you being lucky will be P, this will be 1 minus P. Okay, anyway, this yes and no sort of scenario you see, right? That is Bernoulli distribution. Okay, so the rule is it should have only two outcomes. Okay, either success or failure. Okay, so the Bernoulli distribution therefore describes events having exactly two outcomes which are present in the real life. Okay, it should have exactly only two outcomes. Okay, now suppose we have a single trial with only two possible outcomes such as success or failure. Success probability is P, failure probability is 1 minus P. Okay, and if x equal to 1 when success, x equal to 0 when failure. Okay, let x equal to 1. Fine, then the probability function is given by this. Okay, so for any Bernoulli distribution, as it is a discrete probability distribution, so it will have some PMF, probability mass function. Okay, probability mass function. Okay, so this probability mass function is like what? Okay, so if you see Bernoulli distribution, yeah, as you can see, Bernoulli distribution is a discrete probability distribution. Okay, and that's why we call it as probability mass function. Okay, and if you remember, we tried to have a mathematical equation for every distribution. Okay, so now coming to the mathematical equation for Bernoulli is this. Okay, so the x is, if x is a random variable with Bernoulli distribution, then probability of x equal to 1 equal to p, and probability of, okay, and 1 minus probability of x equal to 0 is equal to 1 minus q. Okay, so then the probability mass function will look something like this. Okay, so it will, the p will be the probability if k equal to 1 and q equal to 1 minus p. Okay, see, are you guys understanding? If you're having two outcomes, okay, either 1 or 0, okay, and if 1 equal to, if k equal to 1, then the probability, I mean the probability is p. Okay, if k equal to 0, it will be 1 minus p. You can call it as q. Q is nothing but 1 minus p. Okay, so if this is, these are the probabilities, this function can be expressed as, okay, this function can be expressed as p to the power k into 1 minus p into I mean p to the power of k into 1 minus p to the power of 1 minus k. Okay, so where k equal to either 0 or 1. Fine, either k equal to either 0 or 1. So if I show you, yeah, so where k, same thing, probability of p to the power of x into 1 minus p into 1 minus x. That means what? P is a probability of success. Okay, and 1 minus p is a probability of failure. Fine. So success, so it means what? Success to the power of the given random variable x into failure to the probability of 1 minus x. Okay, this is a PMF of the probability distribution, PMF of the Bernoulli function. Okay, so here, so what will the P of 1, guys? So if you see P of 1, it will be P to the power of 1 into 1 minus P into 1 minus P. Sorry, 1 minus 1. Okay, what will be P to the power of 1? Okay, P to the power of 1 will be P, and 1 minus 1 is 0. Agree? And something to the power of 0 is 1. So it will be P into 1, 1. Sorry, P into 1, P. So probability of 1, okay, probability of success, we got it as P. Fine. And when you take probability of 0, P to the power of 0. So if you put 0 in this equation, what it will become? P to the power of 0 into 1 minus P into x 1 minus 0. Agree? 1 minus 0. So P to the power of 0 is 1, and into 1 minus P, 1 minus 0 is 1. So 1 minus P to the power of 1 is 1 minus P. 1 into 1 minus P equal to 1 minus P. Okay, so that means probability of failure is 1 minus P. Okay, so these are the success and failure probabilities. So to derive this, you have this function. Okay, and when x equal to 0 or 1, this will be the function. Okay, now as we have seen, for example, if you see a simple graphical representation is, yeah, so if you have a probability of Binomial distribution is actually simple. So if the overall probability will always be equal to 1. Okay, and you will have only two scenarios, success and failure. Okay, success and failure. Fine. So if the probability equal to p of p equal to 0.3, that means what? The success probability, okay, success probability is 0.3. That means p of 1 probability 0.3. Obviously the success failure probability will be 0.7. Okay, that means p of 0. Fine. So here the same thing, p, if here p equal to 0.3, okay, that means here 1, success probability 0.3, that means 30%. Okay, so obviously the remaining 70% will be the, this will be the failure. Okay, this will be the success. This is how you can define and denote simple Bernoulli distribution. Okay, and this will be the variant. This will be the expected mean. Fine. So some of the real examples are result of exam pass or fail, guys. Okay, gender of a new baby, male or female, result of a World Cup, win or lose, tossing a coin, heads or tails. Okay, so these are the like any real life simple yes or no sort of distribution. You can denote it in the form of Bernoulli distribution. Okay, nothing much about the Bernoulli distribution. But now, if you see the binomial distribution, guys, okay, so it is nothing but it is built on the basis of Bernoulli distribution. Okay, so if you perform an event once, it is Bernoulli. But if you perform a series of those Bernoulli events, then the whole series will become a binomial distribution. Okay, but only the point here is the outcome should be independent of each other. Okay, so if you see a binomial experiment is a series of n Bernoulli trials, okay, whose outcomes are independent of each other. Okay, so that means what? You are conducting n Bernoulli trials, okay, n Bernoulli trials, but each of these, each of these trials, the outcome of each of these Bernoulli trials should be independent of each other. Okay, that means the output of second Bernoulli trial should not be dependent on the first Bernoulli trial. Okay, is Bernoulli clear, guys? Before I come here, is Bernoulli clear? This equation theoretical part. Any doubts in Bernoulli?
No, sir, clear.
Okay, so now coming to binomial, right? So in binomial, it is nothing but the same experiment, like which is having yes or no, true or false sort of outcome, that single Bernoulli. If you repeat n times, okay, series of n Bernoulli trials, that will become a binomial experiment. Okay, but the only rule is the whole outcomes are independent of each other. Okay, that means what? For example, let's say I'm taking this class. Okay, we are taking meet AI class. Okay, over here you are having like some students. Okay, student 1, student 2, student 3. Okay, so now if I ask, okay, okay, each one of you, so how is my class? So there are two possibilities, either good or bad. Okay, so student one can say good or bad. Okay, same thing goes for good or bad. Okay, so now each of these events, okay, if you consider only student 1, so the what is the output? Okay, the output could be the random variable could be good or bad. Okay, that's all. So it's a Bernoulli trial. Fine, there is some probability of good, there is some probability of bad, but the overall probability will equal to 1. Okay, so each of these S1, so S1 student, so you can draw a Bernoulli graph like this is good, okay, this is bad. So let's say good is like 80%, bad is like 20%. Okay, this is the Bernoulli distribution of first student. Similarly, the student 2 can also give his opinion, good and bad, and his probabilities might be different. Fine. Similarly, S3, S4, S5. So when you consider each of the single student at a time, that one single event will be called as Bernoulli. Okay, but if you consider this whole S1 to S5, all the students, the whole this 5 Bernoulli events, each individual Bernoulli events combined together will become a binomial experiment. Okay, but the only concept here is the outcome should be independent of each other. That means what? Here, the opinion of this S2, student 2, should not depend on the opinion on S1. Okay, he should take his decision independently. That is the concept of independent of each other. Okay. Getting? That means if just S1 is telling his own feedback from his experience, okay, that will become a perfect Bernoulli. Similarly, if S2, he is also based on only his experience, okay, if he is giving, but not depending on any other student, fine, okay, which completely independent of himself, okay, and not dependency on any other student, his outcome, so that is also called as mutually independent. Okay, So like that, if every outcome, okay, every outcome is independent of each other, that means what? If you toss a coin, you will get heads. Fine. And like that, if you are tossing it 10 times, 10 times you might get anything, but every time it is independent of the previous result. Agree? Every time the value which you are getting will be obviously independent of the previous results. Getting is.
Yes, sir.
Yeah, but if you take another scenario, but if you're thinking, sir, when there will be any dependency, okay, for example, if I just consider there is a basket, okay, in this basket you are having, okay, so like three types of uh, balls, okay, brown, we are having brown two, okay, and we are having blue color two balls, okay, and we are having pink color two balls, okay, for example. Now in this scenario, if I just ask you to, okay, if I ask you to take out uh, a ball which is blue color, okay, which is blue color, fine. So taking one time blue color will be Bernoulli event, because you will get a blue, you will not get a blue. Agree? Simple. Bernoulli will have two outcomes. You will get blue or you will not get blue. Fine. First time you are conducting this experiment. Okay. So first time when you consider this, okay, what will be the probability, guys? The probability to get a blue color bag. Okay. The probability to get a blue color bag is what? So two blue color balls are there. So it will be 2 by, okay, and 1, 2, 3, 4, 5, 6, 6, 2 by 6. Okay. To get a blue color uh, ball will be probability is 2 by 6 first time. Okay. So let's say you have picked a ball. Okay. Randomly you are blindfolded and you have picked a ball. Now there are two scenarios. Okay. One is you got a blue ball. Yes. And second thing is you did not get a blue ball. Fine. So if the second time, again, if you are pulling out one more ball, fine. And if you want to calculate again what is the probability of getting a blue color ball, now it will be different, because in the first scenario, if at all, if you have got the blue color ball, okay, if at all you got the blue color ball, agree, so now this will be absent over here, you will have only 5 balls. So what is in this scenario, considering it as yes in the first scenario, okay, if this is yes, now in the second time it will be what? So the blue color balls will be only 1. So now 1 by total balls, how many? 5. Okay, 1 by 5 will be the answer. But now let's say in the first scenario you did not get a blue color ball. Okay, so you got, sorry, yeah, so you got some brown colored bag, ball. Okay, so now in this scenario, if you not get a blue color ball in the first scenario, so now considering it as no, now what will be the probability in the second time, guys? So you're having two blue balls, so it will be 2 by overall count is 5, 2 by 5. Okay, so getting, so if you see here, okay, if you see here, what happened? The first time the Bernoulli trial, what experiment I'm trying to conduct is the same. My experiment is to take out a blue color ball. Okay, and the out, how I'm saying it is a Bernoulli, because the output is, but it's binary. Okay, either yes or no, yes or no. Okay, so now, but here the problem here is when you're conducting multiple times, okay, so these are not independent, because first time the probability of getting blue color ball, yes and no, will be different. Okay, so and in the second time the probabilities will be again based upon the first time probability. These are going to change, because if it is in the first time, if you take a blue color, it will be 1 by 5. If you don't take it, will be 2 by 5. So obviously there is some dependency, right? There is a dependency. So these are not independent of each other, they are dependent on each other. Okay, so that's why this type of events will not be considered as a binomial trials or binomial experiment, because there is some dependency. Fine. But if you toss a coin, true or sorry, you will get heads or tails. Okay, So even if you toss 100 times, every time, whatever the value result you are going to get, that is completely independent of the previous tossing. Fine, there is no dependency. So in those cases, it can be considered as a binomial experiment. So where you are having n Bernoulli trials, but the outcomes of each Bernoulli trial are independent of each other. Okay. Is the difference clear, guys? Are you able to understand the dependency concept?
Yes, sir.
Okay. Fine. Now coming back. Okay. So for example, consider a fair coin. Okay. Flipping a coin once is a Bernoulli trial. Since there are exactly two complementary outcomes, that means flipping a head or flipping a tail, and they are both 1/2, the probability is half, 0.5, no matter how many times the coin is flipped. Note that the fact that the coin is fair is not necessary. Flipping a weighted coin is still a Bernoulli trial. Okay, Bernoulli, not binomial. Okay, flipping a coin, a plain coin, unbiased coin. Okay, what is the probability to if it is unbiased coin, pure coin? Still the probability, sorry, the outcomes is heads or tails. Okay, heads or tails. But what is the point here? Heads will also have 0.5, tails will also have 0.5. Okay, even if the coin is not a fair coin, okay, even if it is a weighted coin. What does a weighted coin mean, guys? That means the weight on the tail side will be more, or weight on the head side will be more. Usually our coins will be unbiased coins. Okay, it will be equal weighted both the sides. But even if you deliberately prepare a weighted coin, okay, if you put more the metal weight, if you put more on the head side, okay, even then it is a Bernoulli, because the rule for the Bernoulli is just the outcome should be 2. Here also you will have heads and tails, but the only difference is the probability of heads and tails will be different. Okay, because it is more, if it is more weighted on the head side, okay, so the gravity on the head side will be more. So if you have the coin, okay, let's say on the bottom you are having head and the top you are having tails. Okay, if the weight is more on the head side, the gravity will be more, so it will fall to the face of earth on heads. That means on the top you can see tail. Okay, if the weight on the heads is more, so it will be pulled with that direction and heads will be touching the face of the earth. But on the top, okay, you can see the tail as an open end. Fine. So in this case, the probability of the tail is more. It's not 0.5, 0.5. Okay, the tail will be 0.7. This will be 0.3. Okay, but no matter what is the weightedness or fair kind, since the output is 2, it is considered as a Bernoulli trial. Now, a binomial experiment might consider flipping the coin 100 times. Fine. With the result number of hits being represented by the random variable. The binomial distribution of this experiment is a probability distribution of x. Okay. So when you flip this coin 100 times, that will become binomial. Okay. The x is the number of success in a given Bernoulli trial with independent trials, with the probability of the success being p and probability of failure is q. Then exactly k success in the for exactly k success in the experiment, the probability will be right. Okay, so see. Now, for in each trial, okay, in each trial, what is the probability of success p? Failure 1 minus p. Okay, see, now you'll understand why this line is important. Why we are considering the outcome should be independent of each other, guys? Because you are performing Bernoulli trial n number of times. That means in one Bernoulli distribution, okay, in one binomial distribution, you will have n number of Bernoulli trials. Agree? Bernoulli 1, Bernoulli 2, like that. So if you consider as a whole this binomial distribution, fine. If at all the outcomes of each of these, fine, let us just think for a moment, they are independent of each other. Okay, just in the bag example, I've shown they're independent of each other. So what will happen, guys? What will happen? Each time the success and failure probability will continuously change, because 2 is dependent on the 1. 3 will be dependent on 2. Like that, let's say 6 is dependent on 5. 5 is dependent on 4. Like that. Fine. So you cannot have a general value of success or failure. Fine. Because for a single Bernoulli trial, success is P, failure is 1 minus P. Okay, Bernoulli 1. Bernoulli 2 also independent if you consider P1 minus P. Bernoulli 3 also independently P1 minus P. But if at all there is some relation started between these two, 1 and 2, fine, or 2 and 3, these will not be the same because the second time the probability is not P. It is dependent on this and it will change. Again, 3 will depend on 2, it will change. So obviously it becomes completely complex and we cannot have one generalized function because in each of these Bernoulli event inside the binomial experiment, okay, inside this binomial experiment, and for each of these Bernoulli trial, okay, the success and failure probabilities are constantly changing. When they become dependent on each other, when they're dependent on each other, it will be constantly changing. Okay, that's why we consider only those outcomes which are independent of each other. So when it is independent of each other, what will happen, guys? You don't need to worry about the each individual success and failure because they're independent of each other. Okay, so every time, okay, blindly you can consider it as P and 1 minus P. Any number of times you consider this experiment, it will be 1 P and 1 minus P because it is not dependent on anything. Even if you consider 1,000 times also, every time it is happening by itself. Okay, so that is the reason you will consider it as independent of each other. So now if you see the probability distribution of binomial, okay, now same, the P will be the probability and of success and 1 minus P will be the probability of failure of what? Of each Bernoulli trial inside, okay? When you're conducting a binomial experiment, inside that you will have a set of Bernoulli trials, right? So for each of these, if success is P and failure is 1 minus P, okay, then for exactly K success in the experiment, okay, to get K success in the experiment, the probability distribution will look something like this, okay, n k p to the power of k into 1 minus p into n minus k. What are these? N is the number of trials you are doing, okay, 10 times you are doing, and k is the number of success you want, and p and 1 minus p are the probabilities. Okay, see guys, what it is saying. See, let me just put the word. See, okay, so we are good with the Bernoulli, right? So this will individual probabilities. Okay, but coming to binomial, see what's happening in the binomial. Binomial, as I said, it will be just a series of Bernoulli. Okay, so here, if you conduct, okay, if you conduct a binomial distribution, if it is having one Bernoulli, 2 Bernoulli, 3 Bernoulli, like that, n Bernoulli experiments you have conducted. Okay, n Bernoulli experiments you have conducted. Okay, now in this n Bernoulli experiments, each of these Bernoulli experiment will have a success probability of P, failure probability of 1 minus P. Agree? Same thing for n experiments. Okay, n trials. Fine. Now, in first time also you will get success, you might get success, you might not get success. Okay, like that n times. Now, this is K is over here, K is number of successes you want. Okay, number of successes. That means if you take an example, coin, flipping it or tossing a coin is a Bernoulli trial. Do you agree, guys? Tossing a coin is a Bernoulli. Agree?
Yes, Santosh. half of, yeah.
Yeah, it will have heads, it will have tails. Okay. Now, as I said, tossing one time is Bernoulli, but we are tossing n times. All these individual trials now will become a combined binomial distribution. Fine. Each time, if you consider getting a, for example, getting hits equal to success. Okay. You can take tails also success, anything, but I'm taking hits equal to success. That means its probability will be equal to P. Okay. Now, getting tails equal to failure, I'll consider, and its probability will be 1 minus P. Okay. Now, once you consider this should be same, consider same for all the n Bernoulli trials. Okay. So, in second time also, you will toss the coin, heads probability will be P and tails probability will be 1 minus P. Like that, you have tossed n times. Okay. For example, for simplicity, I'll take 10 equal to 10. Okay. That means 10 times you have tossed the coin. Each time the probabilities are P and 1 minus P. P is for the probability of hits, which I consider as a success. 1 minus P is the probability of tails, which I consider as a failure. Are we good till this point?
Yes.
Okay. Now this is done. Now, binomial distribution will say, out of this 10 times, K is, if K is a number of success, that means, let me take K equal to 6. Okay. So how many times, if you are tossing 10 times, how many times your success? That means probability of getting 6 successes. Understanding? Out of this 10 times, what is the probability of getting 6 times success? That means, what is the probability of getting 6 times hits? Agree? 6 hits. Getting guys? First time it could be heads or tails, second time could be heads or tails. Like that 10 times, I don't know, it could get heads or tails with the probability P and 1 minus P. I don't know. But now binomial distribution function, this is saying x equal to k. That means k is what? Number of successes. N is what? Number of trials. So if n equal to, that means if we are tossing, for example, 100 times, if I am tossing the coin, where in each of these 100 times, each of the trial is considered as a binomial distribution. Okay. See, understand this formula, guys. Then you will understand the whole binomial distribution. Okay. See, I'm explaining again. If you are, let's consider tossing of this coin. N is the number of times, number of trials. Okay. Inside a binomial distribution, you will have n number of Bernoulli trials. Okay. Inside a binomial distribution, you will have n number of Bernoulli trials. Okay. So if n is the number of trials, or let's say 100 times you have tossed the coin. 100 times you have tossed the coin. Okay. And in each of these 100, okay, in each of these 100, every single. Your device battery is 10%. Plug in the charger. Yeah, sorry. So each of these 100 events, trials is considered as each individual Bernoulli trial. Okay. For each of the trial, getting success is P. Okay. This is success. Okay. I'll consider as head. Okay. And 1 minus P is a failure probability. Fail probability. Okay. I'll consider as tail. Okay. Each of this. So if this is a probability, success probability, failure probability, and n times you have tossed. Now, what is the probability that out of this 100, I'll get, let's say, some random 44 times I will be success. That means 44 times I'm going to get heads. What is the probability? I want to know. So then K will become 44. Now this will become N, that means 100. K is 44. Okay. That means 100 say 44, guys. So it's a probabilities. Okay. Permutations, combinations. And P to the power of K. P is what? My probability of success to the power of K is what? 44 into 1 minus P. Okay. Into N minus K is what? N is 100 minus 44. So here, P and 1 minus P, what? P is success probability and fail is 1 minus P is failure. If it is a fair coin, hits probability will equal to tails probability. As I said, 50-50, 0.5, 0.5. So P will become 0.5 and this will also become 0.5. If it's a weighted, okay, then it could be 0.3, 0.7, something like that. Getting, guys? Did you understand this formula? Let me know. If not, I will explain this again. But make sure that if understand this formula, okay, if you understand this, that's the binomial distribution. Is the equation clear? No? Shall I explain again?
Understand, Pankaj.
Okay, fine. So I hope it's clear. Now if you see, okay, see what is c to the power of 6 factorial by 6 minus 1 factorial into 1 factorial. Okay, that means 100 44 means 100 factorial by 100 minus 44 factorial into 44 factorial. Okay, 100 this is actually 100 c 44. Okay, it is 100 c 44. Okay, so this mathematical equation you can do, okay, but even if you don't want to do, that's fine. But this equation should be clear. Okay, in binomial, what we are trying to find out, we are trying to find out number of successes. Okay, each time there could be probability of success and failure, but as a whole, what is the probability of getting k successes? Okay, getting exactly k successes you are getting. Okay, so that is a binomial distribution. So for example, if you see, let's flip a coin 6 times with probability of getting a tail 0.3. See here, is this a fair coin or a biased coin? Can someone tell me? When the tail probability is 0.3, is it a fair coin or a biased coin?
Biased.
Biased.
Okay, biased coin, because it's not half of it's not 0.50, it is 0.3, and for that hits will be 0.7. Okay, now let's try the binomial distribution for this experiment. Okay, so how did this become binomial distribution? Now binomial distribution is nothing but a combination of different Bernoulli trials. Okay, and what is a Bernoulli trial here? Flipping a coin is a Bernoulli trial. And how many times you are doing? 6 times you are doing. Okay, 1, 2, 3, 4, 5, 6. Okay, so all these are Bernoulli trials, and combined this is just a binomial experiment or distribution. Okay, now if you see possible outcome, okay, number of tails, so 0 tails. Okay, if you are considering tail as a success, fine. If you're considering tail as a success, so what is the probability to get a 0 tail? Okay, so you getting this? Yeah, same concept here. So here he has considered tail as a success. Now if you consider tail as a success, okay, I'll explain you again. See here. So see, he has considered tail, okay, tail as success. If it is success, okay, then its probability will be P. Okay, and heads will be failure, okay, whose probability will be 1 minus P. Clear? So now, how many times he is saying he has flipped the coin? 6 times he has flipped the coin. Fine. So when he has flipped the coin 6, that means n is 6. Total number of experiments is 6. Okay. And now let's write this. Okay. Now what is the probability of getting? Now what is the probability of getting? We are trying to find out 0 tail. Okay. 0 tails means now k is what? As you can see here, k is the number of successes. Okay, k is the number of successes. Okay, so earlier we have considered 6. Okay, but now the fundamental definition of k is now how many successes you want. Okay, but here what is success? Getting a tail is success in our experiment. Okay, so now k equal to, first time we are checking k equal to 0. Okay, that means 0. Oh, sorry. Now 0 times what is the probability to get k? That means what? Even if you toss 6 times, what is the probability of getting 0 successes? Means success is tails. That means you don't get any tail. All the time you'll get hits only. It is possible, right? It is possible. Anything is possible. So if you toss the coin 6 times, every time you can get heads also. Every time you can get tails also. That's completely possible. So you are checking x equal to 0. So now what will this become, guys? This will become any 6, total 6 times. So this is how you should understand binomial. 6 times you are tossing. Overall experiments are 6. In that, my success is, I'm looking for 0 success. That means I don't want any success. That is a probability. And P, what is a P? P is a probability of success. And here this probability of success is P. Tails. What is the probability of tails, guys? 0.3. Okay. So now it will be P will be 0.3. 0.3 to the power of K. K is 0. And 1 minus P is how much? 0.7. N is how much? N is 6.
6 minus 0.
Okay. Now this is how much, guys? 6-0 means it is actually it is written as 6C0. Okay, this is 6C0. Okay, combinations. Okay, it is 6C0. That means what? 6 factorial by 0 factorial into 6 minus 0 factorial. Okay, and into 0.3 power 0 is 1 into 0.7 into power 6 minus 0 is 6. Okay, 0.7 to the power of 6. Okay, what is this, guys? Whatever the value you are getting here, what is this? This is telling us if you flip a coin, weighted coin, whose tail probability is 0.3 and heads probability is 0.7. Okay, and getting tails is a success. These are the rules of that in each individual trial. Okay, out of this 6 trial, every trial you are considering, getting tails is success, getting heads is failure, and the probability of getting tails is just 0.3. Under these scenarios, if you conduct 6 type of such trials, okay, among those, what is the probability of getting 0 success rate? That means what? 0 times you will get tails. Every time you will get heads. Okay, that probability is this. How much it is? See, 6C60 into 0.3 into 0 into 0.7 into 6 to the power of 0.6. Okay, this is 0.118. Fine. 0.118 is the probability of getting 0 tails among 6 flips. Is this clear, guys? Is 0 tail clear?
Yes, sir.
Yes, sir.
Okay. Same thing goes for any other tails. Now, out of this 6 times, I want only 1 time tail. That means 1 time tail means 5 times hits. Total 6. Same thing. So P of x equal to 1 will become what? 6C1. Okay, 6C61. 0.3 into power 1 into 0.7 into power 5. Okay, this only the equations and this will change. Okay, C60 and this will become 1. This will become n minus 1. Okay, 5. This is a probability. Okay, so like that, getting 2 times tails, getting 3 times tails, 4, 5, 6. Agree? So this is the probability of getting all tails. Probability is this. Okay, and all 0 tails is also probability this. Okay, and which is having the highest probability, guys? As you can see, 0.2. Okay, getting 2 tails is having the highest probability. Okay, because as you can see, just by numbers, if you try to understand, probability of getting tail is less. Okay, tail రావడానికి మనకి ఛాన్స్ తక్కువ ఉంది ఈచ్ ఇండివిజువల్ ఎక్స్పెరిమెంట్ లో కూడా. ఎందుకంటే ఓవరాల్ గా 0.5 ఉండాలి, కానీ ఇక్కడ ఏమైంది? టైల్ 0.3 ఉంది, అంటే హెడ్స్ కి 0.7 ఉంది. అగ్రి, హెడ్స్ కి 0.7 ఉంది. ఒక్క ఇండివిజువల్ ఎక్స్పెరిమెంట్ లోనే టైల్ కి 0.3 ఉంటే, అలాంటి 6 కండక్ట్ చేస్తే ప్రతిసారి కూడా 0.3 ఉంటుంది కదా. అంటే ఏంటి? 6 times heads is dominating tails. In each experiment, heads is dominating tails. 6 times it is getting dominated. Agree? So అలాంటప్పుడు 6 times నీకు టైల్ ప్రాబిలిటీ తక్కువ ఉంది, అలాంటప్పుడు 6 times నువ్వు పర్ఫామ్ ఫ్లిప్ చేసి దాంట్లో ప్రతిసారి నీకు టైల్ రావాలి అంటే ఖచ్చితంగా దాని ప్రాబిలిటీ చాలా చాలా తక్కువ ఉంటుంది కదా. ఆర్ యు గెటింగ్ మై పాయింట్? ఇన్ ఈచ్ ఎక్స్పెరిమెంట్ ఓన్లీ ద టైల్ ప్రాబిలిటీ 0.3. Second also 0.3, third also. So very much less than the head. So now when you're checking this 6 tail, that means who's getting tail probability each time is just 0.3, very much less than the heads. Getting once only it is difficult. But if you are considering 6 times you're flipping and 6 times you want the tail, that means every time if you want to get the tail, obviously the probability will be very much less. That's why it is almost 0, 0.0007, which is almost equal to 0, which is logical because the probability of tail is less every time. Agree? So then that's why if you see 2 out of 6 times, there is more probability to get hits because the probability of hits is more. Okay. So out of 6 times, the probability to get hits is more because the hits probability is more. The probability to get tails is less. That's why out of 6 times, what is the maximum number of times we can get tails? 2 times. See, 2 times tail is 0.324, which is the highest among everything. That means what it is saying, the maximum probability to get number of tails is 2 out of 6. With this probability, you can get only 2 times maximum, and which is also logical, right? ఎందుకంటే tails probability tail side మన probability తక్కువ ఉంది కాబట్టి 6 times చేస్తే 2 times రావచ్చు. Majority will go for remaining 4 times it will go for hits, but 2 times అనేది మనకి tail రావచ్చు. ఓకే, బట్ ఆల్ టైల్స్ కావాలంటే ప్రాబిలిటీ 0 అయిపోతుంది ఎందుకంటే తక్కువ ఉంది. ఓకే, ఓన్లీ 2 అంటే ఓకే మనకి 0.3 times రావచ్చు. ఓకే, అండ్ సిమిలర్లీ ఫర్ అదర్. ఈస్ దిస్ లాజికల్? డిడ్ యు గెట్ దిస్ గైస్?
Yeah, Santosh. If it is tail be 0.3, 0.5 inches, so logically half of the
Correct.
percent we can get. It is less than 0.5 half, so there are 2 chances maybe.
Correct. Correct. So what you can do, correct, what you said is correct. So what you can do, instead of considering tail is 0.3, you can consider it as a fair coin. That means this will become 0.5. With 0.5, if tail is 0.5, obviously head will also become 0.5. Okay, with that you can again do this calculation. Okay, this calculation you can also do just by hand. By hands you can do calculation and see if it is a fair coin, what is the probability then getting 0 tail, 1 tail, 2 tail. Okay, 6 tails you need to 6 times when you're flopping with a fair coin with 0.5, 0.5. If you see these probabilities, then getting 3 getting a tail, okay, 3 times, then the probabilities will be different because it is a fair coin. So you can get, this will be better. Okay, because it is a fair coin, the probability to get 6 tails will be bit better because 50-50 chances will be there. Okay, so that experiment you can do, you will get better understanding. Okay, so looking at the above table, we can find the probability of obtaining k outcomes. Okay, what is the probability of getting XL2 tails is this one. Fine. So hey guys, one more point just now I remember. So actually yesterday and day before yesterday I tried of sending the notes. Okay, notes is ready, but I did not find your email address, guys, because I want to send it over the mail because then it will be forever. So you do one thing. Okay, post this class, you send me your email addresses. Okay, you have sent me on the Google form, but I couldn't find that. Okay, so send me your Gmail addresses so that I will send this document and notebooks, everything. Okay, so make a note of it, don't forget. Fine. So coming back, so you are having, so this is the probability of each and everything. Okay, all flips. Now if you plot a graph, okay, p of 0, p of 1, p of 2, see, 1 is 1.18, 0.3, and the maximum is for 2. Okay, so if you see for the maximum, p of x equal to 2. Okay, and minimum it is p of 6. Okay, for p of 6 it is 0.007. Okay, that means almost 0, and that is expected. You cannot get all tails with a very low tail probability. Okay, is this clear, guys? Everybody?
Yes.
Okay, so now similarly you can also see lots of examples. Okay, so for example, a basketball player takes 5 independent free throws with probability of 0.5 of getting a basket on each shot. Okay, let x be the number of baskets he gets. Show the probability distribution of x. Okay, see, again same experiment. What is the 5 independent? See, this mathematical, see, the statement can be easily converted into mathematical equation. He's saying basketball player is taking 5 independent free throws. That means that became a binomial experiment. How? Because independent, he said. So there is a binomial. Okay, there is a binomial. And in this binomial, we are having 5 independent throws. Okay, 1, 2, 3, 4, 5 independent throws. Each time he's throwing. And each of these throw will become what? Can someone tell me? Each of this independent throw will become what? What type of trial?
I mean, chances, half of chances. It may or may not.
No, I'm saying no. The overall is binomial, but inside that each of these trial will be Bernoulli, right? Okay, fine. Not sure, like Megan or Srisha, are you guys getting the concepts or not? I'm not sure because most of the times you're not responding. Okay, but that's fine. If you're getting, I'm happy. But if you're not getting and if you are not responding, then it will be a loss. Okay, so just make sure. Fine. So now coming to this binomial, so 5 times he's throwing, each of this will become a Bernoulli. Okay, each of this will become a Bernoulli. Fine. So out of this 5, fine. So every time he's saying there is a probability of 0.65. So why it became Bernoulli? When it is become Bernoulli, there will be only 2 cases. One is getting into basket and not putting the shot or no shot. Okay, shot or no shot. That means in the basketball, he's getting a shot or no shot. Fine. So the getting a shot is probability 0.65. And not getting a shot will be 1 minus 0.65. Okay, so like that he is throwing 5 times. Okay, and each time this is the probability. Now if you consider the binomial distribution of this, fine. So now what is the binomial distribution? It will say 5 times you are throwing, each time there is a probability of 0.65. So you can consider how many shots you can get. That means 0 shots. That means 5 out of 5 times you never got a shot. Every time you missed, or 1 time you got the shot, 2 time, 3 time, 4 time, 5 time. Okay, getting? So out of this 5 independent throws, okay, so he got how many? Actually 6 outcomes are there. Okay, are you able to understand? He's throwing 5 times, like a 5 independent free throws, but you will get 6 outcomes because 1, 2, 3, 4, 5 and 0. Okay, so now probability of getting 0 is what? Same concept, C50. Okay, same thing. NPK, this equation you should remember. Okay, so C of 50 into probability. Okay, probability of success is 0.65 and failure will be 1 minus 0.65. Okay, into 5. This is the thing. And 1 basket, 1 time getting shot, 2 time getting shot, 3 time, 4 time, 5 time. Clear? And now if you see the probabilities and if you try to just plot it, see the maximum probability is for 3 baskets. Okay, 3 times to get a shot is having the maximum probability. Okay, next is 4 times good and 2 times, 5 times, 1 time, 0 time. That means most of the time we will get a shot because getting 0 time means missing a shot is having very less probability. That means he's going to get some good shots because each time the probability is 0.65. Okay, is this clear, guys? Is the example and the diagram, equation, concept clear?
Yes, sir.
Okay, cool. Okay, so now this is a distribution and this is a mean and variance. Okay, fine. So the final distribution which we're going to study is a Poisson distribution, guys. Okay, which is a Poisson distribution. Fine, this is also very interesting distribution, but it is a bit different distribution. Okay, so till now what we have studied Bernoulli. Okay, Bernoulli. Okay, and group of Bernoulli will become binomial. That's it. Fine. Now there is a different type of distribution, okay, which is a Poisson distribution. Okay, this is also a discrete probability distribution. Okay, this is also a discrete probability distribution. For example, if you have seen our first class over here, yeah, over here, if you see, you see here Bernoulli distribution, binomial, uniform, Poisson. Okay, so these distributions we are actually looking now. See, normal we have seen, chi-square we will see, exponential is nothing but like constantly increasing, logistic distribution, okay, that we will see, student distribution we will see. But among this, we have seen some log distributions, Q distributions, all these are continuous distributions, right? Coming to discrete distributions, yeah. So we discussed Bernoulli, we discussed binomial, okay. Uniform also we have discussed, okay. And Poisson distribution we are going to see, okay. So this is the complete discrete distributions, fine. So now coming to the Poisson distribution, okay. Now coming to the Poisson distribution, it is a simple distribution, okay. See, but here one important point over is the Poisson distribution is a discrete probability distribution of the number of events occurring in a given time period, given the average number of events occur in the time period. Okay, simple, don't get confused. First of all, it is a discrete probability distribution. That means it is a discrete and the function will be PMF. Agree? It's a PMF, probability mass function, because the random variable is discrete. Here, the distribution is how many number of events will occur in a time period given the average number of times that occur in the time period. This is the only point you need to understand. Then it will be very, very easy. Here we are checking if at all given the average number of times the event will occur in the time period, you want the number of events occurring in that. Okay, that means average it will be given. For example, let's say the number of in DMart. Okay, let me take an example of DMart. Okay, so let's say DMart every Sundays. Okay, every Sundays from 8 p.m. to 10 p.m. you will see a lot of rush. Agree? 8 p.m. to 10 p.m. Okay, average, the average population, okay, average people visitors of DMart on Sundays, okay, 8 p.m. to 10 p.m. let's say it is 50,000, 50k, okay, average. Okay, that's what, given the average number of times that event occurs that given time period, okay, average population, okay, is 50k. Now that is average, that's not exact. Okay, that is average. Okay, that's not exact. But given that you want to calculate the exact number of events occurring in the time period, give on the based upon average, you want to calculate the exact number of events. Okay, exact number of events you can calculate using what we will see. A certain car wash, okay, shop gets an average 3 visitors. Okay, this is just an average. Okay, however, the actual amount might vary. Okay, because you, let's say you have observed, okay, you have observed, okay, 10 Sundays and you said, okay, on average it is getting 50,000. Okay, that is average. Based upon that, you want to calculate the distribution of exact time period. Okay, so we will see, okay, with an example. For example, a Poisson distribution can be used. Okay, a Poisson distribution can be used to analyze the probability of various events regarding how many customers go to the center. It can allow one to calculate the probability of a dull activity where there are 0 customers coming, as well as the probability of high activity where there are 5 or more customers coming. This information can in turn help the owner to plan for this event with staffing and the scheduling. Okay, so if X is the number of events observed over a given time period, then probability of observing K events over this time period. Okay, if X is the number of events observed over a given time period, okay, then the probability of observing K events, K such events, okay, over the given time period is this. See, X equal to K. Okay, X is the K. Sorry, if X is the K, that means K events you want to observe. Okay, so you already observe that X is number of events a given time period. Okay, given over a given time period, that means the same example, like on Sunday evening time. So you have observed K events. Okay, that is average. Now, based upon this, what is the probability of occurring observing K events? Okay, that means if you are getting 50k people on Sunday evenings on the DMart average, now what is the probability of getting, based upon this, what is the probability of getting 1 lakh people? Okay, if average is this much, based upon that average, I want to know for a particular Sunday what is the probability of getting 1 lakh. Okay, and if you do this, what it will help, guys, so it will tell you, as mentioned here, on a particular shop, if you calculate and it will say, hey, what is the probability to for a dull activity? That means what on what particular day the activity is dull. That means on Monday or Tuesday, or on which particular day the activity is dull, so that he can plan accordingly. And on what particular day the probability of high activity, that means it is having like rush. That means most visitors are visiting on what particular day, given the average values. Okay, so that he can manage accordingly. Okay, so now the formula is PK. Okay, and mean or expected rate is, okay, the average is lambda. Okay, And see k, if k, x equal to k, that means you want to observe k events, just like in the binomial experiment. In the binomial experiment, what is k, guys? K is just the number of success. K is what? K is exactly k success you want to get. Out of n experiments, you want k success. That's why x equal to k. Similarly, over here in the Poisson distribution, you have observed out of average time, the k events are observed. But if you are looking for x events are observed in average given time. But out of that, if you want to know the probability of just k events, okay, probability of x equal to k is lambda. This is the average value, okay, into your k events which you want to observe into e to the power of minus lambda by k factorial. Okay. So here over here, if you see the Poisson distribution often uses approximation of binomial probabilities when n is large and p is small. Okay, that means what? N is large, the number of trials is very much large, and when p is small, that means the probability of success is very much small. That means, let's say if you are tossing a coin like 1,000 times, coin is tossed, and out of that the probability of success, that means probability of getting heads is very much small, let's say 0.1. okay, so in this case, the more number of times you are tossing and less number of success, then he's saying you should go for the Poisson distribution. Okay, this is just tweaked around the binomial distribution. Okay, for example, if you see here as an example, you will understand. In a coffee shop, the average number of customers per hour is 2. Find the probability of getting k number of customers in the shop. Okay, so this is what Poisson, as I said, average you will observe, you will get some value. Based upon that, you will find out some exact number of values. Okay, based upon the average. So in a coffee shop, on average per hour, you will get 2. That means you are observed for 2 days or 1 week, you have stayed in the shop and you observed on average per hour, you will get 2 customers. But based upon that, what is the probability of getting k number of customers? K could be anything. Okay, now for example, 0 number of customers, because this is just an average, right? This actual value could be less than this or greater than that. That is the reason it is average. You getting? If the in a class, if the height is ranging from 4 to 6, okay, let's say 4.1 to 6.2, the average height will be somewhere around 5.3. That does not mean everyone is 5.3. It could be less than this or it could be greater than this. That's why it's called average or mean value. Similarly, if the average customers is 2, the what is the actual value? It could be less than 2, or because sometimes no visitors or sometimes will be more visitors, that we want to calculate. Is the theory clear, guys?
Yeah, Santosh.
Yes, sir.
Okay, so same thing. So now he's saying, so with that probability, okay, so with this probability, okay, 2 is the average, 0 times customers. Okay, so if 0, then the formula you need to put it as the average value is what? 2. Okay, 2 and k is power 0 and e to the power of, okay, minus 2 by k is 0 factorial. Okay, so now when you solve that, he's saying you will get 0.13. Okay, similarly when you do for 1, it will be lambda is what? Lambda is mean value, average value is 2, again 2 to the power of 1 into e to the power of minus 2 by k is 1. Okay, 1 factorial. Okay, so like that when you calculate, so these are the probabilities. Okay, probability of getting n number of customers. Okay, so as you can see, see now, if you observe, probability of average value is 2. That means 2 number of customers you are getting 2 is almost highest. Okay, 0.27, because this is the highest. Okay, but that does not mean every time you will get 2. You can get more than 2 also and less than 2 also, but the probability will be less. Probability will be less, because as you go on increasing the number of customers, you can see the probability is decreasing. Okay, because 2 is the average, mostly you will get around 2, but 3 also will get, but with less probability, 4, 5, 6 and 9. But for 9, if you consider, if you see 0.000, see 0.000, almost 0 is the probability to get 9 customers per hour. Getting? So this is a probability graph you can have. So 0, 1, 2, 3, 5, 6, 7, 8, 9. Okay, this is a, it's like a log normal. Fine. So around the probability average value, you'll have the maximum value. But if you keep on increasing the value based upon this average value you have calculated, okay, so you'll get the probability constantly decreasing. Is this clear? Based upon the average value, you will calculate. Okay, based upon the average value, you will calculate. It's not like, so that's the reason. In the Poisson, you should have this. First of all, you should have the given value for average value. Okay, if it is for a given amount, sorry, what is the average number of times it's occurring, based upon that only you can calculate for any given number. Okay, same thing. For example, average, you have went to a zoo. Okay, and you have went to a zoo, and see the average number of elephants seen on a particular day is 6. Okay, what is the probability that tourists will see fewer than 4 elephants in the next day? Okay, the first day you have went to a safari. Okay, and you have seen okay, the 6 elephants. Okay, you have seen the average number of elephants to see in one day, it is 6. Then what is the probability to see? Average is 6, means you can see less than 6 or also greater than 6, that, but the 6 is just average. Now he's asking what is the probability to see less than 4. Then what is the probability of 0, 1, 2, 3, 4 on the next day? Same thing, 0, 1, 2, 3, 4. If you put the if you put this formula, okay, the average is 6. Okay, now x equal to lambda will become 6, k will become 0, e to the power of minus 6 by 0 factorial. Okay, so if you substitute those values, you will get this. Fine. The overall probability will be what? Probability of 0 plus 1 plus 2 plus 3. 0, 1, 2, 3, because he's asking for less than 4. He's asking for less than 4. Fine. So if you add all this, you will get 0.15. Okay. And these are the different type of applications, guys. The number of mutations. Okay, for example, the number of bankruptcies that are filled in a month, or number of arrivals at car wash in 1 hour. Okay, in car wash, you will have if in 1 hour, in 1 hour averagely, if you get 10 cars for washing services, then you can ask for like how many what is the probability to getting 20 cars, like that. Okay, all these examples. Okay, you can see number of visitors website per minute. Okay, so let's say Google. Okay, if you see the Google website, okay, you can say in 1 minute, for example, in 1 minute you see 1 lakh people visiting the Google website. This is the average value. Based upon that, if you ask for what is the probability to see for 2 lakhs people visiting, you will get with less probability. 10 lakhs, less probability. As you are increasing the value, you will get probability will be less. And if you're coming near the average, the probability will increase, because average will have the greatest probability. Getting, guys? Is that clear? Examples, distribution.
Yes, sir.
Okay, fine. So I would say that's all from my end. These are the distributions we have covered. Okay, so we have covered the all the required distributions, what all needs to be covered, guys, regarding the probability distribution. So from tomorrow we are going to start the central limit theorem. Okay, so which will be the next level concepts, and that's all. So as I said, just don't forget to send your email address so that I will share these notes. Okay, and you can revise. Fine, guys. That's for today. Thank you.
Just
Yeah.